introduction. And indeed, please feel free to ask questions. It will be 5 lectures. Today, however, I will not talk much about diffusive systems. I will just introduce some models and the motivation for studying such systems. And of course, will introduce my notation and my way of dealing with this. I learned that there will be a considerable overlap with what Martin Evans told you this morning, but I think it's still okay if I repeat some of the material because it's the same stuff from a different perspective, so maybe it's useful. Okay, so first of all, what are driven diffusive systems? By the way, I can hear a change in volume. Can you hear me? Is that okay? Yeah, because right now it sounds to me as if I was speaking without microphone. Aha. Yeah. Okay. Right. But this means I have to bend down like this, which I can't. Let's see. It's fixed. Yeah, okay. Okay, let's try. How about this? Can all of you hear me? Yeah, is it okay? Okay, let's see. I hope it will work. All right. Okay, so what are trivial diffusive systems? Well, by this I mean classical many-body systems. So we'll not talk about quantum systems. And we will always assume that there are really many particles. Now, this is basically what systems means. However, there are some more adjectives here. For instance, since we talk about many particles, we really want interactions. Otherwise, we would have if we have non-interacting particles, we may just as well talk about a single particle. That's not what we want to do. So there will be interactions between particles. But I will talk only about short-range interactions. And by short-ranged, I mean that they extend over a few typical microscopic length scales of the size of the particles, say. Okay, now, this still doesn't cover driven and diffusive. Diffusive means that the dynamics of these particles are noisy. Noisy dynamics, so not deterministic. As you would have, for instance, from Newton's equations of motion, and driven. That means there is some force acting on these particles that manages to maintain a stationary particle current. So these forces, they could be, so these are really the important ingredients. These forces, this can come from boundary gradients. So you think of a container that's connected to reservoirs with different chemical potentials, and particles can flow through the system. This will induce a current. So this is a generalized force, a thermodynamical force, but you can also think of physical forces between the particles or external forces dragging on the particles, such as an external field like gravitation. It just induces a net drift in the bulk. So these forces, they can be boundary-driven or bulk-driven, or both, of course. So that's, generally speaking, the kind of system that I want to talk about. Now, this kind of system have attracted a huge amount of attention in the last decades. And this basically, major parts of statistical physics really dealt with these systems. And this has many reasons. Well, first of all, in the mathematical literature, these models are usually described by Markov processes called stochastic interacting particle systems. So I write this here in brackets. Stochastic interacting particle systems. And they were introduced in the mathematical literature in the 70s with the following question in mind. Given the system of many, many particles that undergoes deterministic Newtonian forces, as particles do on a microscopic level, how come that nevertheless what we observe on macroscopic scale is, well, quite simple, and we don't see these forces anymore. Think of a fluid or a gas. Its motion is governed by the Navier-Stokes equation. The Navier-Stokes equation, what you have is a density, its velocity field, but there are no particles, no particle positions. On the other hand, we know that gases and fluids are made up of little molecules between which you have Newtonian forces, van der Waals forces, and so on. So, which are of completely different nature. So how come that from these microscopic interactions, you get these macroscopic equations where all these microscopic details have disappeared? How can you understand this? How can you even perhaps derive those macroscopic equations from the microscopic laws? And moreover, the other question is, why is it that these equations are so universal? If you think of the Navier-Stokes equations, well, they're valid for a vast number of very microscopic, very, very different systems. The only thing that changes from system to system are a few macroscopic parameters, such as viscosity or other coefficients, diffusion coefficients, that enter these macroscopic equations. Or a simple example is the diffusion equation. The diffusion equation, well, describes diffusion of, well, almost anything. The only issue that comes up, or the only point where the microscopic nature of this thing that diffuses comes into the diffusion equation is the diffusion coefficient. So why is it? Why is it so universal? So this was one of the motivations for introducing these particle systems, because in these systems, some of these, at least in many cases, one can answer these questions and really understand exactly what's going on. The other reasons for studying these are that, particularly in one dimension, and that's what I will focus on, many interesting phenomena emerge. Forming phenomena that have no analog in equilibrium. This could be phase transitions, which in one dimension, in equilibrium, you do not have with short-range interactions, but it has turned out that in far from equilibrium, when you have these driving forces, they can occur. You can have anomalous transport, you can have spontaneous symmetry breaking, phase separation, the whole host of phenomena that in equilibrium would now be not observed. So it's an exciting field. Also, one can study in great detail fluctuations. One can study universality classes, dynamic universality classes, and one can say a lot in general terms about non-equilibrium behavior, which until a few years ago was quite difficult. So this comes under heading fluctuation theorems, which I will also cover. So these are some of the motivations. On top of that, there are even more, because there are applications. There are applications to biophysical systems, like molecular motors. There are applications to traffic flow, and there are, of course, also applications to other physical systems, like diffusion in carbon nanotubes or in zeolites. So this is just some ideas to give you some idea of why these models are interesting. So now let me explain to you how I want to describe them. As I say, I will take a Markov approach. So I will assume that these stochastic dynamics have basically no memory of their past. So whatever happens now is random and depends only on the present state of the system, not on its previous history. So this is an approximation that is certainly valid on the microscopic level of deterministic laws, but it's a good approximation also for, in many cases, of this in this stochastic picture. So let me just give you this general setting. I have a process, and the different configurations in which the system can be, in general, I will denote by eta. So these are the configurations. So this could be the locations of the particles and the momenta if you describe them, and so on. So in the classical system would be just all the points in phase space. And the set of these configurations I call omega. This is a set of configurations. So this would be, for instance, in a classical system, the phase space itself. However, I will assume, mostly for simplicity, that the omega is finite. So it has a finite number of states, configurations. Okay, so now the Markov process is defined transition rate. So let's make this abstract setting, let me make it concrete in terms of the random walk that you have heard about this morning. So for a random walk, let's say on a ring of L sides, omega is just the set of numbers from 1 to L, just a set of sites where the random walk can be. And my configuration eta is just the location k of my random walk on the lattice. It's the position, counted modulo L. I take periodic boundary condition. Okay, so that's my particle on my ring of L sides. Now, what happens is that I imagine that this particle has a built-in clock. And this clock, this rings, and when it rings, the particle jumps to the neighboring side. That's my dynamics. Now, stochasticity comes in because I say, oh, well, this clock is not a very good one. It's not a Swiss clock. It rings after a random time. And this random time, so I have an internal clock. Rings after an exponentially distributed random time. Exponentially random time with mean that I write 1 over R plus L. So that's the mean time after which it rings. And when it rings, as I say, at a random moment, the particle jumps to the right, by which I mean clockwise, with probability R over R plus L, and to the left, so anti-clockwise, with probability L over R plus L. So that's my random walk. Okay, now that means that the transition rates are R and L. So the transition rates which have been denoted by W, and now pay attention to the notation. I denote it by W K prime K, which is transition rate from K to K prime. So you have to read it kind of backwards. So this, in this case, is simply equal to R times delta K prime K plus 1 plus L times delta K prime K minus 1. So these transition rates, they completely specify my Markov process. I can, from this point on, I can really forget about the random walk and can just think of K as being any configuration eta in some set, and then such an equality will define my Markov process. With whatever is on the right-hand side will define it. So this really specifies exactly, this transition rights specify what Markov process I'm talking about. Okay, now, of course, this is just a definition, so we want to get something out of it. So for instance, since a random process, we are not very much interested in what happens in the single realization. This cannot be predicted, and as such, it's not really a physical object. Physics deals with things that we can predict. So what we can predict, however, is the probability at which a particle will be found at a certain position at a certain time. So we want to compute or say something about the probability pk of t, which is just probability that kt is equal to k. It is the position of the random walk time t that is equal to some number k that we specify. So what can we say about it? Well, according to this definition, one can show, and this I kind of assume that you have seen in the morning, that this probability changes in time as follows through the master equation. So the time evolution is given by the master equation e dt p of k and t is equal to the sum over all k prime in omega except k w k k prime p of k prime and t minus w k prime k p of k and t. So again, I'm kind of assuming that you have seen this before, but nevertheless, let me remind you of the meaning. So this is the change of probability of finding the particle at site k. It increases through jumps into this site. And the jumps into this site come from sites, from other sites k prime, which are not equal to k. And the rate of this jump is k prime to k. And then the total change probability is the rate times probability itself of this other state. This is the gain term. And then you can lose probability, it can become less by all jumps out of site k. So the change then is the probability of being in k times the jump from k to k prime by taking the sum over all k prime where you can go. So this is the meaning of the master equation. So this is the basic object that my analysis starts with. Now you can see that this is a linear equation in P. And in fact, you can define the following objects. So define hk prime k as minus wk prime k for k not equal to k prime. And hkk I write as sum over k prime in omega except k, w k prime k. So you see, these are the objects that enter here. And then I can simply write this as minus sum k prime in omega, in all of omega, including site k, of h, k, k prime, p of k prime, and t. Hang on, is that correct? Yeah, it is, yes. So it's just rewriting this equation in terms of these numbers, including the term where k prime is equal to k, which gives you this one. But now you see what I've written here is nothing but a matrix multiplication. So if you imagine that you put these probabilities in a vector, so define a probability vector So this is my definition. It's all my probabilities arranged in a column vector. And this column vector I denote by the quantum mechanical cat symbol. Right? It depends on time. So if I write this, then I can rewrite this linear equation as d dt p of t is equal to minus h p of t, where the matrix elements of H are those numbers. H, K, K prime is equal to the small k, K prime. Okay, it's just rewriting things. Just using the well-known fact that this is just a system of first-order ordinary linear equations, differential equations, I can always write them in matrix form. That's what I'm doing. Just check, is it clear? Are there any questions about this? Because this really I will use all the time, so if there's a problem, you should really stop me here and ask for an explanation. Is it okay? All right, okay. Good. So let me just make it specific for the random walk here. So for the random walk, we have the rates I have defined here, right? So let me first plug it into the master equation. And then I will write down what the H is. d dt p of k and t is equal to r times p of k minus 1 and t plus l times p of k plus 1 and t minus r plus l p of k and t. Okay, that's my master equation in this form, using the definition. And then, with this definition, H is the following matrix. It's minus, by convention. And then I have minus R plus L on the diagonal, R on this off diagonal, and L on that off diagonal. That's what my matrix H looks like. And 0 everywhere else. Sorry, except here in the corners. Here I have an L and here I have an R. Coming from periodicity. That's really just this one matrix element in the corner. Okay. Yes, there is, oh, hang on. Yeah, it should be like this. You see the derivative is minus h times this vector. So this minus here cancels that minus. So you apply this matrix without the minus sign to the vector, and then the diagonal should be negative, as you can see here. Diagonal term. The reason why I put this minus sign here and again here is because, you see, I wrote this equation with these symbols, not without reason. This reminds me of quantum mechanics. And indeed, we can understand in a formal way, and I stress formal, this as a quantum mechanical equation of motion, where this is a quantum Hamiltonian. In this case, if you take R equal to L, the symmetric case, you will see this is a discrete Laplacian. That's Laplacian. So it's the discrete version of the difference of the space derivative squared. Then this here is nothing but the equation of motion for a free particle in quantum mechanics, the Schrödinger equation, in imaginary time and with h bar equals z to 1. So there's this formal similarity. And this formal similarity extends to other processes, and it suggests to use quantum mechanical methods. Of course, we are not doing quantum mechanics. I really want to stress. So for instance, this object here is not a probability amplitude. It's never complex. It's always real. This is probability itself. But nevertheless, many of the computations that we do in quantum mechanics, such as similarity transformations, the concept of ground sets and so on, they have a meaning here. And you will see some of this. Erase. So let me introduce some of those concepts that are similar to quantum mechanics that we can use. Well, first of all, this equation, the master equation, of course, you can integrate it formally, and you get P of t is equal to exponential minus h times t times P of 0. Right? It's just a simple differential equation. That's the solution. Again, like in quantum mechanics, this is the time operator. Okay, so what do we do with it? Of course, taking the exponential of the matrix is not something that we can normally do. In some cases we can, for the random walk, for instance, we can by diagonalization, but it's nevertheless, generally it's tricky. So we have to introduce some concepts how to deal with this object. Anyway, we are usually not interested in the full distribution. We are usually interested in expectation values. So we have to introduce all these objects in this language. So first of all, my basis, I've already introduced. Basis, BI, is just this canonical unit basis. So this is the canonical basis of the complex vector space with dimension D. And then my probability vector, P of k and t, is nothing but the sum over all k. My probability vector, P of t. It's nothing but P of k and t, bk. Okay, this is just rewriting what I'd written before in terms of my basis. Now, this is the complex vector space with dimension D, and this is the canonical basis. We also need the dual basis. Okay, this object I also write as, let me better call it bk, sorry. This is k, where the 1 is at the k's position k. This, remember, I will call k. My dual basis, I denote by the bra symbol, and I define an inner product f g as the sum over all k, f of k, g of k. Now here, notice again the difference in quantum mechanics. In quantum mechanics, there would be an f star here, complex conjugate. Here, there is no reason to introduce complex conjugation. The inner product is just the sum of the products of the matrix of the components of F. Yep. Yep. Canonical basis of C of CD. Okay, so in particular, I have the orthogonality. K prime k is equal to delta k prime k. That's implicit in here, in this inner product. Okay, I need another object, and this you may not be so used to, and this is the Kronecker product, or the tensor product. Use a new blackboard because I will need some space. Kronecker product of any two matrices A tensor B. Now this is the way how I denote it, and I could write down now the exact definition, but it's kind of lengthy, and I will give you an example. So what you do here in this tensor product, let me just show you by example and you will understand. Take A, the 2 by 2 matrix, And these guys don't have to be square matrices. They can be rectangular matrices. So let's take B just to be a column vector of dimension 3, let's say. B1, B2, B3. Then A times B is equal to the following object. I take my matrix element here, A11, and I multiply it with the vector, with this object B, and I put it in this position. So I have A11, B1, A11, B2, A11, B3. Then I do the same here. A21, B1, A21, B2, A21, B3, A12, B1, A12, B2, A12, B3, A22, B1, A22, B2, A22, B3. So this is dimension of dimension 2 by 6. So you can symbolically write it as A11B, A21B, A21B, A22B, with the understanding that this B here really represents a column, well, another matrix, in this case, just of the form of a column vector. So again, the same recipe you can apply to any matrix of any dimension. Any rectangular matrix will be constructed in this particular way. Another B missing here. Is that okay? Do you want me to give another example? I'll give you one more example. Let's take A, 0, 1, and B take as 0, 1. Okay, well, with the comma. So this is again a matrix of dimension 1 by 2, and this is matrix of dimension 2 by 1. A times B is equal to 0 times this matrix, 0, 0, 1 times this matrix, 0, 1. Okay, so again, this is equal to 0 times B, 1 times B, with B being this object here. So this is the projector, right, in this case, and so on. I will not need this corner product right now, but in a few minutes I will need it. So, and let me give you some more notation. So in this case here, this is actually one of my basis vectors. This is actually the basis vector 2. This is the basis vector 2. Hang on, is that correct? Yeah, it's 2. Yeah. Okay. Okay. One more thing I want to stress. E tensor A is in general not equal to A tensor B, right? You just reverse this, you will get a matrix of different dimensionality, right? This is something I would like you to observe. So we can make tensor products of our basis vectors in this way. So, and we can also make tensor products of other vectors in our space. So, for instance, if I have an object like this, G, then I will just omit the tensor product symbol and write this as F, G. So this is just a piece of notation that we know from quantum mechanics is useful, so I will use it. So again, if you see an object like this, the cat following by the bra, it means this tensor product. Now, you can easily convince yourself of the following. Namely, if you take the sum over all k, you make this tensor product, you take the sum over all your basis vectors, then this will be equal to the unit matrix. just 1, 1, 1, and 0 else. So this is, do it as an exercise to get used to these tensor products. Take L equal to 3 and just try it out with these definitions. It's very good. It will take you a few minutes, but it's worth getting used to this kind of stuff. Okay, so this is basically the linear algebra tools that I need. Now I can go on. I can define more vectors. I define the summation vector. S, which is the sum over all k. So it's just a vector that has a 1 in every component, the row vector. Okay? Now, with this summation vector, I can express a very simple probabilistic identity. Namely, well, we have a process, a Markov process, a particle jumps somewhere with some probability. Now, the probability to jump just to any place in the lattice is equal to 1. I mean, not to any specific place, but if you take the sum of all probabilities, it must be equal to 1. So in particular, this would also be true after a finite time. So if I start my process at some lattice site, and I ask what is the probability of finding it later at some other site, k, well, okay, you have to compute. It's not so easy. But if I ask the question, what is the probability that it's anywhere on the lattice? You can immediately say it's 1, because it doesn't disappear. It must be somewhere with probability 1. That means that the sum of all probabilities will always be equal to 1. It's one of the basic axioms of probability theory. So sum k from 1 to L, P of k and t, is equal to 1 for all times. This is probability conservation. Now, in terms of my vectors, this is simply equal to S P of t. Right? If I take the scalar product or the inner product from a Brillouin vector with a summation vector, then according to my definition here, F is equal to 1, G is P of k and t, just get the sum of all P of k and t, and that's 1 because probability conservation. So this already means something because I know that this is equal to S exponential minus HT P of 0, right? This is just solution of the master equation. And now I can take the time derivative. The time derivative of 1 is 0. So 0 is equal to minus S time derivative of this object, H minus HT P of 0. And this is true for all initial distributions, no matter what it is. That means that S is a left eigenvector of H with eigenvalue 0. As stressed, it is a left eigenvector because I apply the matrix to the left. My matrix H, my generator H of the process, is in general not a symmetric matrix. In the case of the random walk, we already, by already see that it was not symmetric. And therefore, right and left eigenvectors will not, in general, have any simple relation to each other. So we have to always distinguish between left and right eigenvectors. So here we know that there is a left eigenvector with eigenvalue 0, such that this left eigenvector is actually the summation vector. So that's already something nice. Now, there's one more thing that we know. Namely, if you have a finite state space and the Markov chain is irreducible, so there's no subspace that remains invariant under dynamics, then this eigenvector is unique. So for a reducible Markov process, we know two things. A, this is the eigenvalue with the lowest eigenvalue. This is from the theorem of Perron-Frobenius, which I don't want to explain, so this is something you just have to accept. Zero is eigenvalue with the lowest real part Again, since my H is not symmetric, I may have complex eigenvalues. However, this mathematical theorem that's valid for irreducible, well, for matrices that you cannot kind of block diagonalize, implies that this is the eigenvalue with the lowest real part. And moreover, this eigenvector can always be chosen such that all its components are real numbers. Components are real and strictly positive numbers. This larger than 0. And this you can indeed see. This exactly satisfies this, right? It's all 1, strictly positive. So that's a useful piece of information. Because it implies something else. Namely, okay, the matrix is not symmetric. We don't know what the right eigenvectors are. However, the eigenvalues are the same. So that means we also have a right eigenvector with exactly these probabilities. Exists an eigenvector pi such that H, the right eigenvector pi, is equal to 0. Okay, this we can immediately conclude, accepting this Perron-Frobenius theorem, which, as I say, you should at this point just believe. But this, of course, means that exponential minus ht pi is equal to pi, so this doesn't change in time, it's stationary. Moreover, it has real components, so if we multiply z as s pi, just the sum of these guys, then 1 over z pi, let me denote this as pi star, this defines a probability distribution. So pi star. It's the eigenvector with eigenvalue 0. Of H, yes. Yeah, let me write it a bit bigger. So pi is an eigenvector with eigenvalue 0, which means that it doesn't change under the time evolution, so it's stationary. Moreover, well, we have a finite state space, so we can take the sum of all its components, and since the sum of all the components is a positive number because each one of them is positive, we can divide by it, and then this means that each component in pi will be a positive real number between 0 and 1, summing up to 1. That means that this is a probability vector, a stationary probability vector. Say again, please. Oh, this is an assumption. Why is it called? Okay. It means that it cannot reduce to a subset that is invariant under dynamics. Imagine, for instance, as a counterexample, think of 2 random walks on 2 rings, which I describe simultaneously by such a matrix. So in this case, well, it's still a process. I can define transition rates, so I still have a set omega, which in this case would be just a bit bigger, but I can still enumerate it. I can write a matrix, but evidently I can, whatever H I write in whatever basis I choose, I can always choose a basis such that this H is block diagonal. Because these are really independent stochastic processes. And this would be not irreducible. This is reducible, namely to these 2 independent blocks. Or another example, let me give you this one. Let's take a random walk on a single ring. But with rates that are not translation invariant, let me assume that there is a region into which I can jump, and then I make, again, some random walk dynamics inside, but I can never get out of this region. Then this would be an absorbing domain, and then this Markov process would be irreducible only on this subset. Because here I can start here, but I can never go back. So it will have a block structure like this. with some elements here, but it will be 0 everywhere else, and then this would be an irreducible block for which this theorem is true. Okay, so from this consideration, we have two objects, the summation vector and the stationary probability vector. Now let me give you some more uses of the summation vector. Are there any other questions? I'm happy to answer. The second example, yes, yeah. Okay, let me make the picture a little bit bigger. So I take a random walk. Let me now just take a simple example. Take a random walk, not with periodic boundary conditions, only because it's somewhat easier to visualize, it's not periodic. So I can jump, let's say, to the right with rate R, to the left with rate L, everywhere, except, let's say, here, I can jump with the rate R, but I cannot jump back, let's say. This is my process, I define it like this. Okay. So everywhere the same, except on this particular bond, right? This is special. Now what happens? Suppose I start somewhere here. It can go to this point, but once it's here, it cannot jump to the left, it can jump only to the right. So it will always stay in this region. Okay? Now imagine I start somewhere here. I can move, and can move, and can move, can go here, and then can jump here. And then it can never return. So this here is an absorbing set. Now, if you write down the generator, it will be almost what I had written before, except that one of these matrix elements here will be missing. And that means that you have a structure. If I, let's say, okay, this is perhaps, if I take this 1 and this L, then it would have a block here, like this, that we had before. And then there would be, well, another block where this element here, sorry, so this element here. Okay, look, the original matrix would be exactly this diagonal and the off diagonals, right? Now, since they're not periodic, there will be nothing in the corners. Now, since this rate here is 0, this left rate, it means that, hang on, it will be this guy that's actually missing this element. This element. So my matrix will have this structure. There will be a block that's completely 0 here and here. And sorry, here not. Here there's one element R which is non-zero. So this is not completely 0. But I have one subblock which is 0. That means that this is an invariant subspace. So if I start here, it will stay there. And that's exactly where this would not apply, because then your stationary vector will have 0 probability everywhere here, so it will not be strictly positive. But on this subset, so the stationary vector will have non-zero components for the sites that correspond to this subset. Then again it's irreducible. But I can make it reducible by breaking yet another bond. Right? And then I will have, again, such sets. in a way, you can actually even take the non-periodic boundary digit, you can take it as a doubly broken bond. You just say, okay, between here and here, I just make the rate 0. It's the same. So now, as I say, on the fundamental object is the probability distribution, P of k and t, and therefore the probability vector, P of t. So this is basically, if we know this, then we really know almost everything about the process, at least what it is at time t. We don't know how it got there, but we know what it is like at time t. This is in general a huge amount of information, and we do not always want it. For instance, if you think of the air in this room, it consists of molecules. They move in a random fashion, and of course, we don't know the complete state of this room. We do not know all the particle positions and all velocities. We simply don't know it. And in actual fact, we don't care. What we want is the temperature, the pressure, and such things, and how the air moves. This is what we want to know. We don't want to know these details. So we will not always be interested in the full probability distribution. What we will be interested in is in certain average values, which are called expectation values. So expectation values are by definition, so objects of the following type. We take our states, eta in omega, so let me be general again, and we look at functions of these states. So for instance, we have our air in this room. It's a microstate of this huge phase space. We don't want to know all the probabilities for all microstates, but we want to know, let's say, the kinetic energy, which gives us the temperature. So it would be a function of this microstate, namely the sum of all kinetic energies of each particle, right? It would be one particular function. And then what we want to know is the expectation of this object, which is write as EF, and which is by definition the sum over all eta in omega, F of eta, P of eta, and T, let's say, in general. It doesn't have to be time dependent, but this would be E of eta T. Well, okay, so this is just the definition of expectation. Now, let's go back to our inner product. You see, it has exactly the structure of inner product. This is equal to F P of T. By the way, how it's defined. So this gives you kind of the mean value, the expected value of this object F, which could be the energy or whatever. Or it could be the position of the random walk of the lattice, then the F would be just, F of K would be just equal to K. It could be the second moment, and F of K would be K squared, and so on. Right? So this is what we want to know, the average of these objects. Okay, now, however, I can do the following. I can write this as S times the matrix F P of T, where F, the matrix F, is a diagonal matrix, some eta in omega, F of eta, eta, eta. So this would be just the diagonal matrix. I hope you can read this. It's a bit small now. F of 1, F of 2, F of 3, and so on the diagonal. Okay? So this is the projector on state eta. I multiply with F of eta, and I take the sum of all these projectors, and I get a diagonal matrix with the functions F on the diagonal. And then, trivially, if I take the diagonal matrix and multiply with this constant vector, of course I get this exactly this vector. So again, S F is equal to F. Simply just try it out. 1, 1, 1, F1, F2, F3, and so on. Well, this is, of course, equal to F1, F2, F3, and so on, which is F. Okay, it's just trivial proof of this identity. So that means I can write an expectation as a scalar product of a diagonal matrix with a diagonal matrix F inside. So this is something that I will use very often. I will consider some function of my stochastic variable that I'm interested in, energy or position of a particle and so on. And I will construct from this function a diagonal matrix such that the elements, the values of this function are just on the diagonal, right? So this you will see very often. So when you see the symbol with a hat on it, it will mean such a diagonal matrix. Okay, now I can continue. This is equal to S F hat exponential minus HT P of 0. Okay, just use the solution of the master equation. And now I use the fact that H applied to S is 0. So I can write this as S exponential HT F exponential minus HT F of 0, P of 0. Again, this is true. This is equal to S, this object here, because H applied to S gives 0. So this will be an eigenvector with eigenvalue 1 of the exponential of H. Therefore, I can write it like this. And this I simply write as S F, use a hat, yes, F hat of T, P of 0. So this is the analog of the Heisenberg representation of the operator in the classical dynamics, in classical stochastic setting. So F hat of T is by definition exponential HT F minus H epsilon T. And this, of course, will in general not be a diagonal anymore. Right? This is diagonal, but if I take this exponential, the result will be a non-diagonal matrix. So this is a trivial, but also sometimes useful way of writing an expectation. The specific expectation is the transition probability. After time t. So what is this? Imagine I start in a configuration eta. So start in configuration eta and ask what's the probability of finding the system in state eta prime at time t, given that it was at eta at time 0. So then we define P of eta prime t eta 0 is equal to the probability that eta t is equal to eta prime, given that eta 0 was equal to eta. Okay? So this is the transition probability. Start in configuration eta. And what is the probability to be in eta prime at time t, right? So it's this object. It's also called conditional probability. So I condition on my initial value to be eta and I ask what's probability of being eta prime at time t. Okay. So now how can I express this object in terms of these guys here? Well, if I start at time 0 in a specific state eta, then it means that my initial distribution is concentrated on the state eta. It has probability 1 for the state eta and 0 else. That means that my starting vector is just my basis vector eta. This is my initial distribution. So this is the initial distribution. Then I evolve it in time. To get the probability distribution at time t, given that I started an eta. Then I want to know what's the probability of being an eta prime. Now, probability of being in a specific case is the expectation of a delta function, or more precisely, of an indicator function on that state. So the indicator on the state eta prime is a function that is 0 except when eta is equal to eta prime. So the matrix representation of this is the diagonal matrix with component 1 at position eta prime. And that's exactly this projector. So my diagonal matrix I have to put here is this projector, eta prime. Eta prime, eta. So this is the diagonal matrix form of indicator one eta prime of eta, which, as I say, which is nothing but delta eta prime eta. And then, okay, then I have to multiply with my summation vector. Okay, this gives me this probability. Right? So this here is my diagonal matrix, this object. And here's my summation vector. Now you see a bit of the magic of this tensor computation. I would like to remind you, this by definition was a tensor product. However, if I take such a tensor product in this way, that I make scalar products that actually factorizes, this is equal to S eta prime times, this is an inner product now, times another inner product, eta prime exponential minus ht eta. So this you will have seen in quantum mechanics somewhere, and it's exactly the same thing here, even though nothing is summation, this doesn't really play a role, and that's why this notation is so useful. So now what is this equal to? Well, this is again a vector that corresponds to an initial distribution, and of course probability conservation is just equal to 1. In fact, you can do it explicitly. This is a vector that is a component 1 somewhere and 0 else, and you take this inner product, it will just be 1. So this will just equal to eta prime exponential minus ht eta. So I have shown you this kind of complicated derivation of something that's actually quite trivial because I want to illustrate some of the manipulation that you can do. I could have written down this immediately, and let me do it so that you actually understand more easily where it comes from. You start with the initial state eta, you evolve it in time, this gives probability at time t, given that you started here, and then you just project on the final state eta prime. This gives the probability p of eta prime and t, given that you started here. So I think this is a more obvious way of seeing that this is really equal to that, but there is this intermediate step which is quite helpful if you go through it later in your own time to understand what's going on. Okay, anyway, the final result is this one. This transition probability is exactly this matrix element. Yeah. Why is it 1? Well, again, you can see it simply by looking at what this thing is. This is a vector, a column vector with matrix element with entry 1 somewhere and 0 else. Of here, for S, everything is 1. So S is 1, 1, 1, 1, 1, right? And eta prime is 0, 0, 0 with a 1 somewhere and 0 else. So then only one guy remains. 1. Okay. So the last concept that I want to introduce before I then actually come to really particle systems is the following, and that's equilibrium. So equilibrium. So far, I have talked only about stationary distribution that don't change in time. And we know that an equilibrium distribution does not change in time. So an equilibrium distribution will be a stationary distribution. But what is equilibrium about equilibrium? That's what I want to say. Well, in equilibrium, in thermal equilibrium, we say that this equilibrium probability P of eta is just proportional to the Boltzmann rate. Right? This is what we mean by equilibrium, thermal equilibrium. So this is the reason. We have an energy, we have an inverse temperature, and E is the energy of the configuration. So that means an equilibrium distribution is a distribution such that P of eta is equal to, pi of eta is equal to exponential minus E of eta. This is really what we mean by an equilibrium distribution. And then the normalized stationary distribution is probability is just 1 over z exponential beta e, and z is the partition function, just the sum over all eta exponential minus beta prime, which, as explained before, is just this summation vector with the unnormalized probability vector. So that's what we mean by equilibrium. But that's not all. At the end of the day, any distribution we can write as the exponential of something else. So that's not really sufficient to specify what we mean by equilibrium. By equilibrium, we also mean the probability that has to do with time reversal. And this is encoded in what we call detailed balance. Detailed balance, which is the following condition. Means that pi of eta, w eta prime eta, is equal to pi of eta prime, w of eta eta prime. So if you insert this here, this exponential, means that the ratio of the rates between the configurations has to be equal to the exponential of the energy difference between the two rates. That's what detailed balance means in equilibrium. Now, this is a component of a vector. This is a matrix element, so we can write this in terms of probability vectors and matrices. And so let me introduce yet another object, the probability matrix. I hat, which is a diagonal matrix which has the stationary probabilities on the diagonal. And with this matrix, you can easily convince yourself that this set of equations has to be true for all eta and eta prime, can be written as ht is equal to pi hat minus 1 h pi hat. So again, this is a simple exercise to show that with this definition, you get the detailed balance condition. Now, what does this have to do with time reversal and why, therefore, we call it equilibrium? Well, again, this is an exercise that I leave to you. You can show the following. If you take the following object, expectation of f2 of t, f1 of 0 in the stationary distribution, let me just modify the pi's, then this will be equal to f1 of t, f2 of 0 in the same distribution. So that means, and this is equal to f1 of 0, f2 of minus t in the stationary distribution. So you see, f1 of 0, the joint expectation or the joint expectation of f1 at time 0 and f2 at time t in the stationary distribution is equal to similar expectation, but with t replaced by minus t. This is time reversal symmetry. or simply called reversibility. And this defines what we mean by equilibrium. So equilibrium is not a property of a distribution in and of itself. It's always the property of a distribution given a certain process. If a certain process satisfies this relation, then we say that the process is reversible. And then the stationary distribution is an equilibrium distribution. Yeah? Say it again? Yep. Yep. This is f2 of minus t. Sorry. So again, to check this is an exercise for you to go through. You use these definitions. So, okay, let me give you one hint. This is equal to S f2 exponential minus ht f1 hat b star. So this is just by definition equal, and then you should be able to show with all these relations that is equal to that one. This? In red, okay. Yellow, okay. So. Okay, just. Okay, yes, sure. So it's f2 of t times f1 of 0 in the stationary, in the expectation in the stationary state is equal to the expectation in the stationary state, again, same stationary state, of f1 of 0, f2 of minus t. Say it again, please. Correct, yes. Mm-hmm. Yeah. Well, okay, look, but this is done at different times. See, this here is equal to S f2 hat of t f1 of 0, according to the definition I've given before. So I make a measurement at two different times. You see, I evolve in time. It's my initial distribution is stationary, but then I make this measurement and evolve it further. So this vector here, f times this one, will not be a stationary vector in general. Okay, and then before I come to concrete particle systems, let me just introduce the last one. Okay, this is an equality that holds for reversible processes. Of course, I can always compute this object here if I want, and then the left-hand side may be something different. This will not always be true. For instance, as an example, take the random walk with R equal to L equal to W. This is reversible, as you will see if you compute these objects. However, a counterexample is the random walk with R not equal to L. This will not be a reversible process. And you see it because the random walk with the drift always in a on a circle. Okay, this is on the torus or on the ring. There's always a current going around, right? And this tells you that it's not in equilibrium. So this is a simple example, counterexample for these notions where you can actually check this. But nevertheless, we can, of course, compute this object here, right? And then, in general, we can write G transposed is just define it as pi hat minus 1 h pi And then we say that G is the generator of the time-reversed process. You can easily convince yourself again that this G will have all the right properties of a stochastic generator. It will have negative off-diagonal elements, which are the transition rates. All of them will be negative. And it will have S as a left eigenvector, so it will generate a stochastic process, and we call this process, the time-reversed process. Okay, so I want to spend the last 15 minutes on introducing the parting system that I actually want to talk about in the remaining lectures. So again, I want to stress something which is sometimes not so clear perhaps. An equilibrium distribution can be called equilibrium only if we have a process associated with it. The distribution in itself, we cannot say whether it's equilibrium or not. This is really important to understand. Okay, so now I have just taken as an example a single particle, a single random walk. Now let's look at interacting random walks. And let me just define one. So again, I take a ring, and I introduce to you the Katz-Leibowitz-Spohn model. Yellow is, yeah, okay, all right. So Katz-Leibowitz-Spohn model. And I define it only in one dimension. It can be defined in any dimension, but I will again go on a ring, on a torus. So torus TL. So a ring with L sides and periodic boundary conditions. Now I have, again, random walks, but not just one, I have many random walks. So I have interacting random walks. And I assume a particular form of interaction, namely exclusion interaction. Exclusion interaction means that each lattice site can be occupied by at most one particle, so it's a hardcore repulsion. Exclusion interaction. Just a sec. TL is just a torus with L sides. So L sides. Torus. Torus means ring. It's the same thing. In one dimension, it's the same as a ring. But again, these models are often treated in more than one dimensions, but still on a torus. So that's why I keep the term. Say again? Yeah, usually a torus, you think of a two-dimensional object like a tire, but this is just a one-dimensional version of it. It's a linear object with periodic boundary conditions. It's the same, yeah. Hardcore repulsion means that exclusion means only one particle can be per site. At most, one particle per site. No, so what is my state space? Well, each site is either occupied or empty. So the state space is 0, 1, L to the power L. It's just the configurations that I can label by occupation numbers. So eta can write as a string of occupation numbers So a configuration, I can specify the coordinates of parties if I want, but I choose not to. I choose to say which site is occupied and which is empty. So I have a local occupation number, which is 0 or 1, and then this array of all this configuration will be my configuration of my particle system. Okay? So the dimensionality, this is my omega. So now my omega has dimension 2 to the power L. It's cardinality 2 to the power L. There are 2 to the power L such states. Obviously. Okay, so I have to specify now the transition rates. Let me write down the transition rates. Well, let me first make a picture, then it's easier to see, and then I'll just write down the formula afterwards. So I have nearest neighbor jumps as before, as for the random walk, right? But they go as follows. They depend also on the next nearest neighbor sites that I have. So if I have this starting configuration, but now I really want to use 2 colors, is green a good color or a bad one? Green is probably bad, no? What's the experience? Not good. Pink, okay. Can you read this? Is it good? Okay. So, suppose I have site K here. K plus 1, K plus 2, K minus 1. Then this particle can jump to the right. It's conserved. But I haven't described the dynamics yet. You will see that it's conserved. Yeah, for a fixed n, you have a smaller number, that's true. But I just count irrespective of particle number. See, if I have 0 particles, it's 1 configuration. If I have 1 particle, I have L configurations. If I have 2 particles, I have L choose 2 configurations. And so the total number of all configurations for all possible particle numbers is 2 to the power L. So, a rate particle can jump to the right if both next nearest neighbors are empty with the rate that I call R times 1 plus delta. And then I have all other combinations, namely 0, 1, 1, 0, 1, 1, and then similar for the jumps to the left, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so here's always the right jumps. And here I look at the left jumps. So they can go to 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Right, so these are always jumps to the right. These are the jumps to the left. See that there are a total of 8 different rates. And I write them as follows. R times 1 plus epsilon, R times 1 minus epsilon, R times 1 minus delta, times L times 1 plus delta. I'll move aside just in a second, then you can copy. Okay, so these are my rates. Okay. So that's my process. You can see that okay, and all other jumps are forbidden. If I want to jump on a site that's already occupied, I just can't. This is impossible. So that's my process. So let me just, in case you get something wrong, let me write down the formula, then you can reproduce this. The rate, W eta prime eta, at site for a jump from k to k plus 1, or between k and k plus 1, is equal to R times nk bk plus 1. So introduce bk is 1 minus nk times gk eta of delta and epsilon plus L times nk plus 1 bk times g eta k of delta minus epsilon times delta eta prime eta k k plus 1, where eta k k plus 1 is equal to n1, n2, nk minus 1, nk plus 1, nk, nk plus 2 to nl. So it's a configuration where particle numbers k and k plus 1 are interchanged. And g k eta of delta and epsilon is equal to 1 plus epsilon nk minus 1 minus nk plus 2 plus delta 1 minus nk minus 1 minus nk plus 2. So that's just a formula for all these numbers that I've written down. Okay. So the last 2 minutes, I want to explain how I choose my basis, and then tomorrow we'll talk about this model. So I have a basis now, which has this, I have a set which has this product structure. Okay. Well, no, I'll do this tomorrow. It will take too long. Doesn't matter. So, okay. Then we finish here. And tomorrow I will continue with the description right now on the generator and giving you some, tell you what the session distribution is. Then we will look at the large-scale behavior of this problem and the question that I mentioned, namely, how come that on macroscopic scales we can say something about the system which is of some generic validity. That will be the topic of tomorrow's talk. The motivation? Okay. Yes, well, if you look at it, you will see that, well, let's take delta equal to 0 first, right? Delta is equal to 0, you will see that the model tries, and let's say epsilon is positive, say, then it tries to create pairs. You see, this can easily create a pair, but then the back process has rate 1 minus delta, so you cannot break this pair easily. So it models an attractive interaction between particles. So it's a hardcore repulsion, but a nearest neighbor attraction. On the other hand, if epsilon is negative, it's a hardcore repulsion and a nearest neighbor repulsion as well. So that's the motivation for introducing the epsilon. And then the motivation for the delta is, it tells you something basically about the mobility in the environment. If you have a low density environment, you can jump more easily if delta is positive than in a high density environment. So it models some kind of friction, if you want. I mean, this is the motion to the right. Motion to the left is actually, it's opposite. It's a kind of non-symmetric situation. This process, you will see, is the time reversed of that one, this part. Yeah, say it again. Yeah, okay, right. So this is W eta prime eta at k and k plus 1. So it's the rate of jump from eta to eta prime for at this location k and k plus 1. So it's some function that depends on the local occupation numbers times this Kronecker delta. That means that the target configuration from which you start, so this is a function of eta. Right? So this is, let me just explain the structure. This here is the function f of eta, which gives you the rate of jump from eta to eta prime, but this eta prime has to be exactly this configuration with the occupation number is interchanged. So only then will the rate be non-zero. And the rate at which this happens to the interchange configuration is exactly this function of eta, which is written in this table. So if you insert these occupation numbers that you see here, then you should reproduce those numbers. This would be this function here. This would be the W eta prime eta k plus 1. It's this column here. And just give an example, perhaps. If you just take the first one, right? Let's first look, what is the G? Nk minus 1 and Nk plus 2 are 0 in the first example. So the epsilon doesn't enter. This is 0. This is 0. Yeah, and this is also 0. Again, so we have 1 plus delta. Is the G. G is 1 plus delta, okay? Now, nk times pk plus 1 is 1, whereas nk plus 1 dk is equal to 0. So it remains is r times 1 plus delta. That's why you have to leave this. Say it again, please. Which? B? Why B? D, W. W, you mean? This one here? No. B? Ah, okay. Ah, here. V. Sorry, yes. V is 1 minus nk. Look at the first example, bk plus 1 is 1. Because nk plus 1